A swarm of thousands of disconnected data points lacks any obvious structure. We're looking for the invisible mathematical gravity pulling these particles into groups. In the real world, information arrives in bulk and without context. We gather billions of raw data points, millions of sensor readings, past customer behaviors, or raw image pixels that arrive entirely without any predefined categories. This scatter plot shows how raw data typically looks, a field of uniform dots. Most machine learning relies on an answer key to sort this out, but here we are moving into the frontier of unsupervised learning. Without labels, the machine must identify patterns based entirely on the internal geometry of the data. To recognize a pattern, it must find the mathematical similarity between these points on its own. A primary tool for this task is a remarkably elegant algorithm known as K-means clustering. The machine starts with zero context. It has never seen these categories before, yet it must define them through nothing more than the physical distance between points. The primary objective is to take this completely unorganized field of information and pinpoint its hidden centers of mass. This grid represents a simple two-dimensional coordinate space. We have 6 unassigned data points, A through F, and an empty assignment table. We begin by declaring K, the number of clusters to find. Setting K to 2, the algorithm drops random red and green cluster centers onto the graph. We then use squared Euclidean distance to measure the straight line proximity between every point and these centroids. In the first step, every point calculates its distance to both centroids. Each point is assigned to whichever center is physically closer. The scatter plot reveals our first colored groups. But since the initial centroids were random, these clusters remain mathematically imprecise. To improve the accuracy, we move to step 2. We look at the red and green groups and calculate the actual mean, the center of mass, for the points currently in each cluster. Notice the shift on the plot. The red and green x's slide toward the middle of their assigned groups. With new centers, distances change. We remeasure every point against the new positions, causing boundary points to switch groups. The machine iterates, assigning points, calculating the mean, and moving centroids until they stop shifting. In this final plot, clusters are stable and centers locked. This achieves minimum within cluster variance. The distance between points and their mean is minimized. The data is sorted. However, this process relies on a human assumption. Clustering is what mathematicians call an ill-posed problem. The machine is a literalist. It will divide the data into however many pieces you ask for, even if those divisions don't exist in reality. If you tell the algorithm to find 10 groups in a dataset that naturally only supports 3, it will fracture the clusters into meaningless subsets. It forces a structure that isn't actually there. To find the correct balance, we use the elbow method. This allows us to mathematically discover the natural number of groups hiding in a specific dataset. This graph plots the total variance, or loss, against the number of clusters. The line drops quickly at first, but at k equals 3, the benefit of adding more clusters begins leveling out. That bend, the elbow, reveals the most efficient number of groups. Unsupervised algorithms are powerful, but they require the operator to identify the point where adding more complexity stops providing clearer insights. These mechanics are the backbone of digital image compression. Instead of storing every unique color value in a high-resolution file, the system groups similar pixels together and replaces them with a single centroid value. This preserves the core information while reducing the required storage space. The algorithm doesn't create the order. The structure was already present in the data. The math simply provides the framework to see it. But even the best algorithms can fail in isolation. Next time, we'll look at ensemble methods and explore how a consensus of hundreds of models can solve problems that a single machine could never manage alone.